All right, everybody. One thing you will notice is that I generally, when I'm doing this, I'll kind of talk louder than normal to make sure that the microphone picks me up. So if it sounds like it seems like I'm shouting.
So should we talk?
The cord doesn't go that far, so I don't have a I could, and a lot. You'll see that today. A lot of times, instead of me walking up the middle aisle, I'll walk more over here. So. All right. To start off for today, I want to start us off with this picture. Okay. Why do I start off today's discussion with this picture of the population density of Ohio? Pierce, go ahead.
Because yesterday you said you were going to start class with that picture.
Okay, good. So at least I'm not a liar. Right? Why else would I start class with this picture? Allison, go ahead.
Because Cleveland is the most populated.
Technically, Columbus is the most populated, actually. But, you know, so, go ahead.
The densely unpopulated areas are like the shells.
Okay. Yesterday in class, we talked about Schrodinger's model of the atom. Okay? And Schrodinger's model of the atom said what? What was the gist of Schrodinger's model of the atom? Do we remember that from yesterday? Caroline, go ahead.
That the location of the electron we can't know for sure.
Good.
Yes.
We can't know for sure where electrons are, but we have a high probability of finding them in certain locations. Just like if we wanted to find somebody in Ohio, right? Just by looking at this map, could we tell where somebody is? Not actually, but if we wanted to find somebody, would we have a good idea of where to start looking? Right? The dark blue ones are the high population density areas. So if we wanted to find somebody, we'd start looking in those dark blue areas, right? You know, Cleveland, right, there's Cleveland, right, what? Yeah. Columbus, Cincinnati, Dayton, good. Akron. Have you ever been to Bayfield? You can see the lake from everywhere in Bayfield. Canton, okay. Anybody? Youngstown. Strongsville, yes. Toledo.
No.
Cedar Point. All right. Anyway, but the point being that there are certain areas in Ohio where we're more likely to find people than other areas. That's the thing that Schrodinger is saying about his model of the atom. I don't know where electrons actually are, but I have a good idea of where we can find them, a high probability of finding them in certain areas. Is it possible that they stole the car and drove to Mexico? We discussed yesterday. It's possible. I know. Apparently Parker went to Mexico. I didn't know. So. Alex, do you have a question? Or are you good?
Yeah.
Okay, go ahead.
No, is that Schrodinger, like the guy with the cat? If it's dead or alive, we don't know if we put it in a box.
Right. But then by actually looking at it,
I know if it's dead.
Well, yes, but isn't it? I don't know the whole Schrodinger's cat thing. I can't remember it off the top of my head. But like, by looking at it, you necessarily change it. Does that make sense? And just like yesterday, we talked about like, by quote unquote looking at an atom, that energy that we use to interact with electrons, we move them. Does that make sense? Did I use you as that example? I can't remember it, but I can't remember. But anyway, so but that has something. It has to do with that. All right, let's look at. Okay. Yesterday, I believe we started talking about. Yesterday, we started in on this. Is that correct? Okay. What we're going to do today is, just like here in this map of Ohio, we call these places where we're most likely to find electrons Cleveland, Columbus, Cincinnati, Dayton, Youngstown. We call those, that's what we call the places where we're most likely to find people in Ohio. What we're going to do today is we're going to start putting names, or at least identifying where these places are in an atom. Is that good? Go ahead.
Is that red circle like the capital?
The red red circle, it doesn't show you here, the red circle is the population center of Ohio. So that's like the average location of all the people in Ohio.
Okay.
Right.
I was gonna say, because if that's the capital, it should be down.
Yeah, there's Columbus. So more people, actually Columbus is a bigger city than Cleveland, if I'm not mistaken, especially now because Cleveland has lost a lot of population. But the population is still located in the northern half, or at least a greater percentage of the population is still located in the northern half, although the city of Cleveland is actually shrinking. Yes, sir.
Why?
Why is the city of Cleveland shrinking in
Yeah.
population? Because people keep moving out of it.
Why?
Because there's no jobs, government is somewhat corrupt, and there's no real good house. So
You live here?
I live in Avon. I don't live in Cleveland. You live in Westlake. You don't live in Cleveland.
Well,
That's the city of Cleveland is actually losing
Like the
population.
actual city.
Yeah, people are moving out of the city of Cleveland because there's no jobs. The government is
because
somewhat
of-
corrupt, and all those
okay.
things. Yeah. What? Yeah, there's not a whole lot of good places to live if you want to do certain things like raise families and stuff like that. I suppose that all depends on your opinion of what a good place to live is if you're raising a family, but yeah, the actual city of Cleveland is losing population, but the
Well,
population is
because we have
still,
like Toledo
yeah,
and
Toledo, Youngstown, Akron, Canton.
yeah. And in the
And,
south, they
yeah, in the south they have this. So they have this area right here. Oh, so they have that
and
area.
they like farm and stuff. So
They
the
farm
kids
and
are,
like they farm and let wild animals roam free.
yeah.
So yeah.
Their population's high.
Yes. Yeah. Like if we had a population map of hikers in Ohio, like
They're
there'd be some at the zoo and then down here in Zanesville. Zoo, 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 and then Zanesville.
Oh, okay.
Is this
Over here. You ever been here before?
No.
Not much there. So once you get past Toledo, pretty much farmland. Yeah, like once you get past Toledo, it's pretty much Indiana light.
Then we'd be like 5 million.
This
And
I think is Findlay. I think that's Lima.
where's Westlake?
Westlake is like
Lima?
Westlake is the last city in Cuyahoga County.
That big white spot.
Lima, that's where
There's parks and stuff
Oh,
right now where people don't live. So. All right, that's actually a good question.
Wait, which one is the zoo? Which one has a really good?
Columbus has a really good zoo. Cleveland has a good zoo.
I don't know.
Toledo zoo is all right. You know.
It's nice.
Okay, so okay. Yesterday we got into this a little bit. Okay, there are ways that we identify or distinguish those different areas where we're most likely to find electrons within an atom. The first way we do that is what we refer to as the principal quantum number. Okay? If we think of the most probable location of an electron as its quote-unquote address, the place where we're most likely to find it, the principal quantum number relates like to the city where we'll find that electron. Okay? If we look at this picture, right, of what Schrodinger's model of an atom looks like, or what Schrodinger thinks an atom looks like, right? While there are dots pretty much everywhere, there are certain areas where there's more dots, and those are our higher probability places of finding an electron. First, we have these big rings, right? There's one real close to the nucleus, there's a little one farther out, a little one farther out. Okay? Those are our principal quantum numbers. We use the lowercase letter n to identify that. Okay? Good with that so far? Yeah, we got through that yesterday. Yes, Allison. Go ahead.
so just like dark spots are symbolized by N.
Yeah, like this part here, that would be like n equals 1. Because it's the first principal quantum level, or first principal energy level. Then this,
Are those kind of like the shells? Or
yes, they're kind of like the shells. They're like the rungs on Bohr's ladder, kind of. But remember that now it's not just the rungs, but kind of like the rungs on Bohr's ladder. So like this is the first principal energy level. This is the second principal energy level. This is the third principal energy level. Okay?
Are the electrons always going to different principal energy levels?
They can, although like we talked about with Bohr's ladder, where they prefer to be
at the bottom?
as close to the nucleus as they can get, because that equates to lower energy. And that'll become more important tomorrow when we start talking about electron
It's like-
configuration and stuff like that.
It's like a city. Everybody wants to be close to like a city.
Except in Cleveland. But yeah, but no, same, exactly, like that. Usually we find population density closer to the city,
Yeah.
and then it gets or less and more sparse on the way out. Okay. Urbanization, exactly. All right, good there? Okay, here's where it starts getting a little tricky. Got that? I don't want to scare you, but this is where it starts getting a little tricky. Okay. If we take a look at our map, even in the city of Cleveland, right? So let's go and take a look here. Okay. And if I zoom in, so if I zoom in on the area that we consider to be Cleveland, what do you even see within that area? There are some white spots, but then there's also some really dark spots, right? What do you think some of those really dark spots might be? Apartments, what's probably not. Seeing how this is based off of census data, they don't have a whole reliable, like, you know. But if this is Cleveland, what do you know is kind of like directly west of Cleveland? What do you run into?
Suburbs.
Suburbs, but which suburb
Cracker
first?
Park.
Not quite yet. Lakewood. Right? What do you know about Lakewood? You ever been to Lakewood before? How close are the houses together? Pretty close. How many people live there?
And they're like two houses.
Right, there are like two houses and stuff like that, right? The population density in Lakewood is very high. Okay? There's more likely to be people there, right? But if you come out a little bit farther west, right, out here to like Westlake, there's still a lot of people, but not as many people as there is in Lakewood. And what we find out is that within this city, even within the high density population city, there's still areas where there's more density and areas where there's not as much density. Even from this picture, you can kind of see, right, there's a couple of white spots there, right? Okay? We have parks in Cleveland, right? Okay? There's places where people don't live. That population density in that area is rather low. If we're trying to find somebody's house or trying to locate somebody, would we go look in the metro parks first? Probably not. All right, good there? And what we find out is that's a lot like atoms. That within each principal energy level, there are areas that we refer to as sublevels. That within those big rings, there's areas where there's more dense and less dense. Within the big ring of Cleveland, there's Lakewood. Okay? And then there's the metro parks. Symbolized by lowercase letter L. A lot of times, if I'm just like writing it freehand, I'll use it like a capital, like a cursive L, just to, so it's. But I didn't do that here. That's lowercase L. So,
Oh, that's a lowercase.
yeah, lowercase L. Okay. Yeah, it does. That's why a lot of times when I just write it, I write it like cursive L. Okay. Within each principal energy level, areas with greater electron density exist. Like we said, within the big city of Cleveland, there's a Lakewood, right, where there's more density. And then there's, Westlake, where there's not as much density. And then there's, like, the Big Creek Reservation of the metro parks, where there's, like, no density. Okay? Here, go ahead.
It's not like people spread out.
Right, exactly. Within that big ring, it's not evenly spread out where we'll find electrons. Okay? Go ahead, Alex.
Wait, so like what is this? Like was this made by like Schrodinger?
It's not so much that it was made by Schrodinger. This is all based on observations. Okay? How we got to these observations, you don't necessarily need. You're not responsible for that right now. Okay? But this is what Schrodinger is seeing. Is that from his equations, he can calculate where an electron came from based on some observations that get made about light and things like that you don't need to worry about right now. Okay? But yeah, this is data. He's finding that electrons exist in these areas more often than others. Okay? You there?
So this is kind of like helping like to find out the location, even though we can't find out the exact location.
Right. that, you know, he's finding out that in this specific instance, it was here. In this specific instance, it was here. And in doing that a bazillion times, we find out, oh, more often they were in these areas than they were in those areas. But every once in a while, there's a dot way out here. Does that make sense? Okay. All right, I'm going to do this in a little different order than I've done it before. See if it works a little better. Let's start off with an x-axis and a y-axis. We're making a graph, right? To see relationships, to see patterns, blah, 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 blah. Okay? Make this a little bigger. Okay. Origin. Nucleus. Okay? Nucleus at the origin. I wouldn't necessarily... So, I believe does the back of your notes have a big empty space? There's that space.
Oh,
Okay.
yeah.
So, let's not draw this just yet. You might find this helpful later on. Okay. Let me draw it first, then we'll explain it more. Okay. All right. Starting off, what we find out is that real close to the nucleus, there is a spherical section where we're most likely to find electrons. Okay? Are we going to find a lot of electrons here or not a lot of electrons here?
A lot.
It might make sense that we would find a lot of them there. However, what do we know that electrons are trying to do to each other? They're trying to repel each other. But the nucleus, having a positive charge, is trying to what? Pull them in. If we start putting too many electrons within this little space, this red circle here, what are they all going to start doing to each other? There aren't that many in this little red space right here. Okay? As a matter of fact, we'll find out there's only two. Okay? But it's closest to the nucleus. We said that relates to low energy. Even though there's only two electrons in this space, where do electrons go first if they can? Right here. Okay? Now, a little bit farther out from that, we'll go green. There's another spherical section where we are likely to find electrons. Okay? And a little bit outside of that, there's an area that kind of looks like figure eight almost. Now I'm kind of like cutting it in half, okay? But notice these are both the same color, yes? Okay. The red represents principal energy level 1. Okay, that's like the first ring, that first dark circle on Schrodinger's picture. Yes? No? Do you want me to go back to the picture?
No.
Okay. Allison said no. That's principal energy level 1. This part, right there. Notice, what shape is it in? What shape is it? It's a sphere, right? Circle, sphere. Okay. Oh, that picture is three-dimensional. I can't draw a picture.
It looks like there's a lot of them.
Yes, but remember, Sam, those dots represent the location of an electron at a specific instance in time. Each one of those dots represents like one measurement that we took of a certain amount of light, blah, 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 you know, okay? That represents the location of an electron at a certain instant in time. But what we see here is that if there's only two electrons, and there's a lot of dots in that space, where are those electrons most often? They are moving around, but are they moving around in a whole lot of space? No, they're almost always in that spot. Okay.
So
Next one out. This one, okay, that ring that we see on this picture, that's my green stuff. Okay.
n equals 2.
That would be n equals 2. Good. And what we'll see in just a second, though, that within n equals 2, okay, there are some L values. Other places within n equals 2 where we're likely to find electrons. Sublevels. Yes? Okay. Get rid of that. Okay. So, Allison,
Yeah.
what's blue going to represent?
N equals 3.
N equals 3. But within n equals 3, there's some L's. There's a big circle. Then there's this one that kind of looks kind of like a figure 8. And then there's one that sort of looks like an X, which I know doesn't kind of look like that because I'm drawing a 3-dimensional representation in 2 dimensions. But it kind of like goes from here to here and here to here. Okay? And these are all sublevels that exist within the n equals 3 big level. All of this blue stuff, all of the blue part of this drawing exists within this ring. Does that make sense? Go ahead, Elsa.
So sublevels are like smaller levels in the like main n equals 1, 2, 3.
Good. Yes, that's what they are defined as. Hence, sublevels. Okay? All right. Let me go this order. All right. Yes, go ahead. Yes, sublevels are the lowercase l. Okay? So I don't think we've written down anything on sublevels just yet, have we? Okay. So let's start here. I think I wrote down this part, right? Okay. So sublevels. Allison, Chris, like you guys just said, those are the areas within the big levels where we're most likely to find electrons. Okay? Cleveland is n equals 1. Lakewood is a L within that big N. Does that make sense? Okay? All right. What we find out, I'm going to skip that just for a second and take you to this picture, which you guys have, I believe, on page 2 of your notes. All right. So what we find out is that within those big sublevels, okay, within those big levels, the sublevels take certain shapes. Okay? S is the spherical one. That's the one that's sort of the first sublevel within that main level. And then I told you there was one that kind of looked figure 8-ish, yes? Okay? We refer to that as a P sublevel. Okay? If we go back to this drawing, green like that. Like that. Okay? Does that sort of make sense? What these two things are? Okay? Now, it looks like that sort of impinges upon the red and the green sphere. And it kind of does. Okay? But there's some areas outside of that green sphere that are more populated than other ones.
What's in the green sphere?
Electrons are in that green sphere. So there's some electrons here, Sam. Okay? And then there's some electrons here. Okay?
Yeah.
That's it. More likely to find electrons in those places than other places.
So you're
But
more likely to
what we
find in the like 8 or in like the
yeah, within this area, on the green sphere, but maybe not so much like here-ish. You know, maybe not so much like right there.
okay.
Okay, if you're watching this at home, I want to make sure you know where I'm pointing. Okay, we don't necessarily find electrons there a whole lot. Even though that may be within the big green level of n equals 2, we just don't find electrons there a whole lot, right? That's the park, right? That's the metro parks. Okay? It's within the city of Cleveland, or the area we call Cleveland, right? But it's just not a lot of people live there. Okay?
Yep.
Caroline, go ahead.
So which circle, like the red, green, or blue, represents
let's go, each one of them represents Cleveland. Okay, actually, no, sorry, shouldn't say that. Okay? This would be, red would sort of be like, let's say like, you ever been to like Lima or Findlay before? Okay, that's like Findlay, all right? Are there a whole lot of different places in Findlay? There's really not, right? All the houses kind of look the same, right? There's some, it's kind of like a downtown area, but maybe it's not exactly right, okay? Then green would sort of be like Youngstown, okay? Youngstown has like a downtown area. It's not as big as like a Cleveland downtown area, but it also has a couple of suburbs like Boardman and Poland and places like that, okay? Blue, now we start getting into places like Akron, okay, where it has like a downtown area, that's like the circle, okay, and then it has like Cuyahoga Falls, right, which kind of, and then it has like Barberton, okay, places like that. So these are like, we're increasing the size of the city, but if we're increasing the size of the city, that means that we have more specialized areas where electrons can exist. Does that make sense? Okay. Awesome. Go ahead.
So like, but like for the main like level, like n equals 1 and
Yep.
2 and 3, the sublevels, wouldn't they have less electrons than the actual n equals 1?
Now, yes. Sorry. No. Because as we get farther out, Allison, we said, how come the red circle doesn't have that many electrons?
Because they like move a lot in this small area. So
What are they trying to do to each other?
push each other away.
So because they're in such a small area, are there many in there? No. But Allison, as we start getting out to the green area, right? What is there now more? There's
So
more
like,
space.
with the farther out ones, like the big blue circle, represent like ones with higher population.
Not necessarily higher population. There's more places where the electrons can go.
Cleveland or something, like a lot of different restaurants. Or
Right.
like
Yeah, there's lots more opportunities.
Yeah.
Right? Does that make sense?
Mhm.
Okay. How are we doing so far? We okay with this? Not really. Okay. There's probably some of you that are at the not really stage, and that's all right at this point. Chris, go ahead.
Is there always gonna only be 3 ends?
No. There's actually, what we'll find out, we'll start doing this a little bit more tomorrow, there's 7 ends, okay? Technically, Chris, there's an infinite number of ends. It's just a matter of, are there electrons actually there? Does that make sense? Here we're talking about spaces. These are kind of like apartment buildings, but it's a matter of, okay, the apartments exist, but do people actually live in them? And that's what we'll get into a little bit more tomorrow. Okay, we know these areas all exist. Are there electrons actually there? And then we'll talk about it. Now, but we talked about the idea that, like in the lights, right? Electrons jump up and fall back down. If one starts here on the red circle, right? It can jump up to here. It can jump up to this part right here. That spot exists, even though there may not be an electron in it right now. But once it jumps up to here, what's it want to do? It wants to fall back down to the red circle. Does that make sense? So those places actually exist, but are there electrons there or not depends on how big the electron is, how big the atom is, how many electrons that we have to place, that kind of stuff. Okay? Alex, go ahead.
So is n basically like the location of the electrons, but like we can predict almost?
Kind of, yeah. But that's the big area. Once we can make a better prediction, like it would be like if you're trying to find somebody, oh, they live in the Cleveland area, versus oh, they live in Lakewood. Does that make sense? Okay. We're getting more specific. Okay. Good. Here we go. Right on. Oh, good.
Alright, you said earlier that you could only have like 2 electrons on n equals 1.
Sure.
I'm gonna be on like n equals 2.
Okay.
N equals 3.
Hold on 1 second for that. I'll show you. I'll tell you just a second. Caroline, go ahead.
What does the like spot with the green overlaps the red represent?
It represents me trying to draw a 3-dimensional stuff in 2-dimensional space.
So like would it kind of be like it like gets really small and it
Yes.
and then like it gets bigger?
Yes. Yeah. exactly like a dumbbell. Yes, you'll see this referred to a lot as dumbbell shape. Okay. All right, Allison, go ahead. One more, then let's move on.
Okay, sorry. So for like the N1, N2, N3,
Mhm.
those like the blue and the green and stuff, are those like borders or are those made up of electrons too?
The lines I drew on this picture are approximate borders to where those electrons can live. We said these are not set in stone, right?
Yeah, like
There's no actual defined area. It's just like a general kind of area. Technically, where could we find electrons? I can find it anywhere on this picture, okay? But we find them more often in certain spaces. More often either on this blue ring or within this blue figure 80 shape, okay? Or within this one that actually kind of looks like an X, and I'll show you that in a second, okay? But just not so often do we find them here. Stone. Does that make sense?
Yeah, and in the blue, there's more electrons there because it's a wider space.
Right. Yes. Okay. That's good.
Do the borders kind of represent the rungs on the ladder?
Actually, red, green, and blue are more the rungs on the ladder. But what we find out is that within the rung on the ladder, you have some leeway about where you could be.
So
You don't necessarily have to be on the rung. You can be a little bit above the rung or a little bit below the rung. Does that make sense? But the red would represent one rung of the ladder. The green would represent another rung of the ladder. The blue would represent another rung of the ladder. All right. Let's go here. Okay. What we find out is, or what we use to represent these different shaped orbitals are these values for L. Okay? So, if L equals 0, that represents an S orbital. S is the spherical one. L equals 1 for the p orbital, L equals 2 for the d orbital, L equals 3 for the f orbital. Okay? This stuff you already have written down, is that correct?
Yeah.
Okay. All right, so here's our general shapes. Okay. Oh, there's our general shapes for what S, P, D, and F would. Don't worry about F; it's pretty complex. Okay. But this stuff is kind of important. Okay. The first sublevel in each principal energy level, that's what PEL stands for, is labeled as S. What's the first thing I drew in every color? I drew a circle first, right? Because what are S orbitals shaped like? They're shaped like spheres. Every principal energy level, every rung on the ladder, has an S orbital. Okay? Every city you go to, regardless of how big or how small it is, has like a main street, right? What your main street looks like might be a little different depending on what city you are, but everybody's got a main street, okay? It's got shops, it's got the post office, things like that. Say again? Police station, fire station, things like that. Every city has one of those, just like every energy level has an S orbital, okay? I didn't draw a red figure 8, right? Because the p orbitals, come on, too many touches, doesn't want to do it for me, too many, there we go, let's go back one, this would be good to watch, okay, so, we don't start getting p orbitals until you start getting to the second energy level. The first principal energy level, PEL, doesn't have a p sublevel. Why? How big is it? It's just small, right? We don't start getting a second sublevel until you start getting to the second principal energy level. Okay. Good there?
Is that L equals 1?
L equals 1. So if we start putting names or trying to distinguish one from the other, okay? Let me go here. So let's take this, the red sphere. Allison, what's N for the red sphere? N1. Okay, so this is N equals 1. And then what shape of orbital is it? It's a sphere. And what L number did we give the spheres? 0. So this is n equals 1, L equals 0. Let's look at this one. Allison, what n level is this circle? That's n equals 2, but what shape is it? No, not the figure 8 one. It's a sphere, so what is the L value? The L still equals 0, but it's different from this L equals 0 because this is in the first energy level and this is in the second energy level.
Now, how do we label the figure 8?
Okay, now with the figure 8s, okay, we said that P sublevels, which are the figure 8s, are labeled with L equals 1. So if we go here, if we take this figure 8 right here, what n level is it in? It's still n equals 2, but now what kind is it? The figure 8, we said, labeled with L equals 1. Does that make sense? All right, everybody. Good work today. Excellent, fellow. Really well done.
Everything homework?
That sheet I gave you, but I'm not sure how much you'll get through.
Dominic, what's up?